Howdy! In this video today, we're going to look at sets and intervals, two types with discrete numbers and also with real numbers. So first, let's talk about set notation. This is going to give us a way to write our answers. So a set, very broadly, is a collection of objects. And those objects could be anything. Could be numbers, could be letters, could be a set of colored rocks. But it's a collection of objects. And in math, we call those objects elements. And also in math, because element starts with E and we like to shorten the notation of things, we have made a little symbol like this. Looks kind of like an E, but it's like a sideways U with a line through it. That means element of. So that little symbol right there means element of. So when you say A element of S, exactly that, it means A is an element of the set S. In normal terms, that just means A is in S. A is in a set called S. And then if it has a slash through it, of course, that would mean A is not in S. So let's do a quick example here. Let's suppose that S is the set containing -2, 0, and 4. Just want to keep it simple right here. You could say -2 is an element of the set S, but 1 is not an element of the set S. So sets, notice we always write them in these little braces here, and we just list the elements inside of them. Order does not matter. You don't list the same number twice. So for example, if you have a group of objects and 0 is in your group of objects twice, you would only write it once in set notation. Okay, and there's two types of notations that are frequently used where we list out elements. That's roster notation and set builder notation. Both of these work great when you're able to list out the things in your set. If you have a discrete type of list or a countable list, perhaps, or it could be uncountable, it could be infinite, but something that you can distinguish between the elements very easily. So in roster notation, that means you just start with a brace and you just list out your elements. So for example, if A is the set of positive integers less than 7, well, positive integers start at 1, so that's 1, 2, 3, 4, 5, and 6. I'm not going to include 7 because it does say less than 7. Set builder notation is just a little bit more advanced. What we do is we introduce a variable. I'm going to call it, let's say x, the set of all x, such that it's denoted with a tall vertical bar, sometimes a colon. And then you can write how to describe x, such that x is equal to 1 or 2 or 3. And it's a short list, so I'll just list them all out. Any one of those numbers. It's the set of all x such that x is equal to any of those numbers. All right, that's set builder notation where you define a variable and then describe that variable. All right, unions and intersections are next. So a union of two sets is the set of all elements that are in either set or both. The set of all elements, whoops, there we go, elements in one set or the other or both. And their intersection, that's the set of elements that is just in both of the two sets that you're considering. Where do they overlap? Where do they intersect, right? So that is the set of all elements that are in both sets. So let's take a look at an example, of course. So if A is the set containing the numbers 1, 3, 5, and 8, and B is the set containing the numbers 3, 5, and 7, we're going to find and simplify the following sets. This first notation with the upside down U, that is intersection. So let's go write that in here. That means intersection. And over here on the next example, a U, U for union. It's a really wide U, not quite like the letter U, a little bit different. All right, A intersect B, that's the set of elements that are in both sets. So scanning along, element 1 is in A, but it's not in B, so it is not in their intersection. 3 and 5, however, are in both, so that set would contain both 3 and 5. And 8 is in A, but not in B. 7 is in B, but not in A, so it is just that set, 3 and 5. A union B, that's the set of everything all put together, right? In A or B or both. And the order does not matter technically, but I'll just go low to high because that's kind of typical, makes sense. And I'm not going to list anything twice. So we do start at 1, and then we'll include 3, and we will include 5, and next is 7, and then 8. Okay, now those are one type because you can just list out the numbers, right? Those are discrete numbers. But sometimes we have infinite sets. So many sets, such as the real numbers, cannot be represented in roster notation where you just list everything out because there's infinitely many and they're all so close together, right? How do you tell? How do you count the next number, right? What comes after 3/4? Right? There's infinitely many decimals. You can always get a little bit closer. So anyways, we cannot list them out. One thing we can do is draw a little number line, and we can just represent it as the set of all numbers from positive infinity to negative infinity. Usually negative infinities on the left, positive infinities on the right. And you can talk about all of those numbers. This is decimals, fractions, positives, negatives, anything just about that's not imaginary, right? So the set of real numbers between 3 and 5, which is an infinite set, it can be represented on a number line or by an inequality or an interval notation. So here's a blank number line. What we're going to do is just call this right here, we're going to call that 3. We'll call that little mark 4, and we'll call that 5. And of course, beyond that would be 2 and 6, and so on out in each direction. So the set of numbers between 3 and 5, that would mean not including 3 or 5. We're going to put an open circle there. We're going to shade in all the numbers in between 3 and 5. So the answer is not just 4, right? 4 is the only integer in between 3 and 5, but there's infinitely many little decimals and fractions all in between 3 and 5. So we can just shade them in. There's no way to list them out, right? You can write it as an inequality. You could say the set of all x, this is with set builder notation, such that x is between 3 and 5. You could say in a compound notation, you could say 3 is less than x is less than 5. And that means that x has to be bigger than 3 and less than 5 at the same time. In interval notation, we start with a parenthesis because we are not including 3. We would say 3 comma 5. That means from 3 to 5 and all the numbers in between. Okay, so that's just a preview to this right here, an interval. Interval is a set of real numbers. A closed interval where we do include the endpoints, we use brackets. So a closed interval includes the endpoints and uses brackets, and an open interval excludes those endpoints, which is what we just saw a moment ago, and uses parentheses. So here's a nice little chart here of several different types of inequalities, right? So you've got the interval notation over here. If you want to label that, that is interval notation, written in set builder notation, and then a number line graph, right? So for example, I'm just going to pick out a few here. The interval from A to B with parenthesis A comma B bracket means numbers bigger than A, but also less than B. So numbers in between A and B, not including A, but possibly including B. You can use interval notation with infinities, which is really handy, right? So for example, A to infinity means all the numbers from A to infinity. So bigger than or equal to A. Another way to write that is the set of all x such that A is less than or equal to x, and it would be graphed like so. All right, so those are just pointing out a couple of things there. Okay, so now let's express each interval in terms of inequalities and then graph the interval. So the numbers from -1 to 2 as an inequality, let's use set builder notation. We can write it as the set of all x such that. Now what we want to do is describe x, right? X can include -1, but not include 2 because it has a bracket on -1, but not at 2. We always put the smaller number first, so we're going to put -1. And we always only use less than or equal to signs when we do compound inequalities. So we go left to right, essentially, low to high. And just like that. All right, if you're going to use a number line, you're going to need to label that number line. So I could call that -1, 0, 1, 2, -3. The next one would be -2, right? And the way we would draw that is we would put a closed dot on the -1 because we are including that number in our set that we are discussing, but we are not going to include 2, so we would put a open circle right there. All right, next we have the numbers from -3 to infinity. So that would mean the set of all x such that x is greater than or equal to -3. You can also write it like that. That is the one case where I would flip the sign and use a greater than sign, as if you're only talking about numbers bigger than or equal to a particular number. So to graph that, you just put 3 somewhere on your number line, put a little closed dot to include that, or -3, excuse me. We're talking about all the numbers greater than or equal to that number right there. Okay, so there's 3 different ways to express each of those sets. Now, last thing we're going to do is combine all of these. So here's one where you have 2 different sets, right? This has a set of numbers over here and a set of numbers over here. So we have the set of numbers from -5 to -2, including the endpoints. So we would start with a bracket in interval notation, -5, comma, -2. Now, we also want to include the numbers from 3 to 4. So it's like all of these numbers over here or those numbers over there. It's not an and, it's technically an or statement, which is a union, the set of numbers in this set or in this set. So or bigger than 3. So we would put 3 to infinity there. So that's how we would write that one in interval notation. Okay, and now we're going to simplify these 2 expressions that are given in interval notation and also graph them on the number line. So, for example, the numbers from 0 to 4 intersected with the numbers from 3 to 6. Now, that's a little bit tricky because intersect means the set of numbers that are in both of those sets, right? So here's one way to do it. We could graph the numbers from 0 to 4. So I guess let's call that 0, 1, 2, 3, 4, 5, and 6, since those are the numbers we have up here. All right, so from 0 to 4, we're not including 0, and we're not including 4, so it would look about like that. Then from 3 to 6, we are including 3, and then all the numbers from there to 6, including 6. The overlap, the set of numbers in both, is only from there to there, 3 to 4. That's it. And it looks like both sets of numbers do include 3, so we will put a bracket on that. And only one of the sets includes 4, so we'll put a parenthesis there. Now keep in mind, y'all, there are infinitely many little real numbers in between 3 and 4. Think of your decimals, right? 3.1, 3.2, 3.14. You've got pi, right? So all of those numbers, there are infinitely many. It's uncountable. We cannot list them. So we can draw it, we can write it in interval notation or as an inequality, but that's it. You can't list them out because there's too many. Okay, last, let's take that same set, but the union, right? The union is where the set of numbers in one or the other or both, right? So we're going to start at, see what we'll do is we'll just kind of graph it up here, right? Their union is all of those numbers, okay? Excuse me, so that would be from parentheses 0 all the way up to 6, and we will include 6 because it is included right there. That's all your numbers in one or the other or both. All right, that is it for sets and intervals.